Hello and good afternoon, everyone. Thank you for joining us today and welcome to today's webinar. This is the fourth webinar of the 5G MOBIX's webinar series on results and lessons learned on 5G for CAM from the project's trial sites. So far, we have looked into the trial sites of Finland, France, and Germany. And today we have the opportunity to get an insight into the Dutch trial site. I hope you can see my screen now. Super. My name is Sevi Christoforou. I'm a Communication and Dissemination Officer with ICCS, the Institute of Communication and Computer Systems in Athens, and I'm also the Dissemination Task Leader for 5G MOBIX. I will be moderating the webinar for today. So before we get started, I would like to inform you that you have the opportunity throughout the presentations to submit your questions to the question box that you can find on your control panel, and we will collect them as we go and take them all at one time towards the end. Now, in case you're experiencing any technical issues with the audio or not seeing the presentations correctly, for example, feel free to use the chat box that you can find again on your control panel to notify the organizers. Now, for introducing the agenda, the program for today, I would like to ask the presenters to turn on their webcams. Hello. Thank you, and a warm welcome to you all. Our first speaker for today is Sven Janssen. Sven Janssen is a senior consultant for automated driving at TNO Traffic and Transport. He has been employed in the automotive domain at TNO since 1990 as a follow-up of his study on vehicle technology at the Delft University of Technology. During his long career, he has been involved in control development for vehicle safety and automated driving, including a full-scale SAE Level 5 truck in 1998 and an autonomous AGV in 2002. More recently, he has been organizing local trails and demonstrations in the Netherlands as part of EU projects C-Mobile, Autopilot, and 5G MOBIX. Currently, he is one of the TNO representatives in the CCAM partnership, following his lead role in the working groups on road safety and cybersecurity of the CCAM platform. Today, he will introduce us to the 5G MOBIX project, and he will also share his conclusions at the end of the webinar. Next, we have Geert Kakis. Geert is a technical lead for Feed Labs at KPN. He has contributed to different 4G, 5G for connected and automated mobility projects such as Concorda, 5G MOBIX, and 5G Blueprint. He has studied at the Technical University of Delft in the field of information and communication theory and graduated in 2001. Today, he will introduce us to the 5G MOBIX Dutch trial site in relation to 5G for CAM challenges. Next, we have with us today Johan Schoolers. Johan is a principal scientist in the automated vehicles team of VTT Technical Research Center in Finland. He has worked over 20 years in the field of road safety and connected and automated vehicles. And currently, he is involved in several projects related to piloting of connected and automated driving, such as 5G MOBIX, 5G routes, and 5G Safe Plus. He's also assisting the Finnish authorities in the Nordic Way projects and participating in several C-Roads technical task forces. Today, he will take us through the use of collision avoidance using maneuver coordination services. Our fourth speaker for today is Peter Paul Shachman. Peter Paul is a senior project manager and lead within TNO on the topic of connected mobility, making the connection between the ICT and mobility domains within and outside TNO. He has over 10 years of experience working on the field of smart mobility, managing, but also being the technical lead for both national and international projects, with the most recent ones being MobiNet, Intercore, 5G MOBIX, and 5G Heart. He's also active in the C-Roads platform, and today his presentation will focus on extended sensors considering slicing and V2X quality of service. Last, but certainly not least, we have with us today Joost de Outen. Joost is a project manager and researcher on artificial intelligence for CCAM and robotics with the Eindhoven University of Technology, and also has a background in control systems engineering and vehicle dynamics control. He has worked in the automotive industry since 2007 for DIF, Pants Powertrain, and TNO. He has also been involved as a technical lead for the TU Eindhoven pilot site in the EU project Autopilot, and has extensive experience working as a technical project manager for past and ongoing EU projects. In 5G MOBIX, he's working on the remote driving use case, specifically focusing on vehicle development and execution of trials regarding positioning. And today, his presentation will focus on remote driving using various network configurations. Thank you all for being here today, and I'm looking forward to seeing your presentations. I will not take any more of your time, so Sven, the floor is yours. I will make you the presenter.
Okay, Sally, thank you for the introduction. Can you see my screen?
Yes, we can see your screen.
Okay, I will go into full scale mode. First, I will give a very short general introduction, and this is the overall agenda for today. So that will be followed by an introduction more on the technical level by Geert Kakers from KPN. And then the three different use cases are addressed and presented by Johan, Peter Paul, and Jos. And finally, we have some conclusions and a summary. So just as a general introduction, the trial site in the Netherlands, it's located at the test site for cooperative mobility in Helmond. This is also the location of TNO, and we have already quite an extensive infrastructure related to CITS, and several 5G networks have now been set up and are operational. The use cases that we have been addressing in the Dutch trial site addresses all categories that are defined also in the 5G MOBIX proposal. So they're ranging from providing traffic information, vehicle control support, and also going towards full remote control over the vehicle. The focus has been to study the continuity of services using state-of-the-art 5G configurations, and considering cross-border settings that we can recreate since we have two networks available. Below here you see also the role of the consortium partners. So we have AI in Motion providing the vehicle for remote driving, KPN concerning the development support of their pre-commercial 5G network, Siemens providing test site support and support in several use cases with their test vehicle. TNO is we are the trial site lead, but we also lead the use case on extended sensors, and we have our own research standalone network. TU Eindhoven, well, they're in charge of the remote driving use case, and also the development of the millimeter wave network, which is used for positioning. And finally, VTT. They're the lead for collision avoidance, and they actually also contributed to the Spain-Portugal cross-border site. So all these partners are from the Netherlands, with the exception of VTT. So they visited us several times with their test vehicle driving from Finland to the Netherlands. Okay, so this is my general introduction. I think now the next presenter is Geert Kakers.
Yes. Thank you, Sven.
Yes, thank you, Sven. Can you can I share my screen?
Yes.
Okay.
I think you'll be able to share your screen now, right? Right, super.
Okay. Great. Yeah, so I will take you a little bit further into the challenges we see and we're trying to explore within the project. Maybe first to start with the overall goals we see. So within Europe, a lot of parts have been working on the 5G strategic deployment agenda. And this is a picture that is taken from this strategic deployment agenda, and here you see all the different corridors in Europe. And well, the goal is, this has been created with a shared vision with a wide group of stakeholders. It is meant for connected and automated mobility, and the goal is to have uninterrupted 5G coverage along the main transport path in Europe by 2025. And then, well, to make this happen, there's also some CEF funding that is being provided by the European Commission to help stimulate these corridors. And of course, to make this happen, we need an ecosystem of different road operators, OEMs, service providers, and of course also the network providers to really enable common services along these corridors. To make this happen, you see that of course the part is mostly at the borders to make sure that the corridors will also work when crossing a border. And to further explore this, there have been different 5G projects subsidized by the European Commission. The first wave is 5G Croco, 5G Carbon, 5G MOBIX. And of course, we are part of the 5G MOBIX projects. And the second wave that has started later on is our 5G MET, 5G Blueprint, and 5G ROUSE. So from 5G MOBIX, we are especially looking at how can we establish these common services across our borders in Europe. 5G MOBIX is quite a big project. We have a lot of countries involved, even outside the European Union, in Asia, and 2 cross corridor sites. And so between Spain, Portugal, and Greece, Turkey, there are some cross corridors where we really have a real border and able to cross this border with different networks. A lot of automated vehicles and different use cases. And if you look at the use cases, we've adopted the classification also specified by 3GPP, so advanced driving, vehicle platooning, extended sensors, remote driving, and vehicle quality of service. And those are the 5 use cases that are categorized and also adopted by the 5G MOBIX project. I will come later to these use cases further. When looking to come in and be able to support 5G connected and automated mobility services, we see some challenges. And I want to mention the main challenges. The first one is roaming interruption. If you currently cross the border in Europe, any country around the world, you will see that you have a interruption of several minutes. So you will lose your data connection for several minutes before roaming to the new network. We see that there's a lot of latency involved, especially when roaming to networks. You see the latency will increase, and especially when you use connectivity and mobility, you need low latency for a lot of use cases. Low coverage in a lot of countries in Europe. Still, there are some highways and places where you don't have any network coverage. And of course, when you depend on the coverage, this is a very this is a thing you need to solve. Service continuity is an issue. Yeah, you need continuous services. Also, when the network is crowded, you need to be able to depend on your network. And when you change networks, you also need measures taken to be able to keep connecting to your service. So these are as issued, and then the last one is the position accuracy. The vehicles depend on an accurate position, and this needs to be kept also in urban situations, so where maybe the satellite communication is not always that good. So we need ways to increase positional accuracy, also in places in tunnels or other places where the accuracy might be difficult to achieve. Looking at the solutions for these different challenges, for the roaming interruption time, we are looking in MOBIX to a seamless handover. This is especially done at real borders, at the cross-border corridors, but also in the Netherlands, in Dutch trial site, we're looking at this using release and redirect technique. For the latency, we can use local breakouts to break out traffic at a business network. But also you will need peering agreements between operators and cross the border, such that if you cross the border and you have a handover to the new network, you can still rely on the regional interconnects to keep the latency low after the handover. Low coverage. There's only one way to solve this, and that is building more infrastructure, building more sites to be able to enable coverage, or maybe use satellite communication. For the service continuity part, there are different things to use. Slicing can be used to guarantee some services, and so to guarantee maybe a certain uplink or latency requirements. Session and service continuity can be used to keep your service also when you move to a different edge location. And of course, there's also a tight integration with the application needed, so the application can respond to different networks and different IP addresses. And also there are different technologies for. And then the last one, position accuracy. We are looking at 5G positioning. And so you have an extra way of getting your position using the 5G network. From the Dutch trial site, we are looking especially at seamless handover, at search continuity, and at the 5G positioning. I think those are the three main things that we are focusing on. And it's combined with different use cases. So for advanced driving, we look at collision avoidance by exchanging MCM messages. We will have another presentation after me on this. The extended sensors is about sharing sensor data, and remote driving is about controlling a vehicle remotely by a remote operator. Each of those use cases have different requirements of the network, which needs to be solved and be able to give them. We have well, this is the area that we're operating in. You see here a road that goes from Eindhoven towards Helmond. And in this road, we have curated a network. If you look at here, we have two base stations. Those are the KPN base stations, creating a 5G SA network with a local edge. We also have one TNO base station is in the middle. It's also connected to a local edge. This way, we have a virtual border between the two networks. So we can do trials here, trying to have a handoff between this and the other node when traveling on the road here. And there is a other network with the TUE campus, and this is mainly focused on the 5G positioning trials that we're doing. So this concludes my slides on the introduction. I think we'll move now towards the collision avoidance by Johan.
Thank you, Geert. All right, let's turn to Johan.
Yep. Hello, good afternoon. So I will speak to you about the collision avoidance using the maneuver coordinating service, which we piloted in the Netherlands. I will first briefly say what's all about and the scenarios which we have tested both in the Netherlands and in Spain, Portugal. Briefly the evaluation results, and then some words about the tests which we did in Spain, Portugal. So our user story's name is Cooperative Collision Avoidance, and we use the 5G to exchange messages with low latency in order to avoid these collisions, and these messages are called maneuver coordination messages. We basically are testing two different approaches, one in which the vehicles negotiate between each other using the 5G network. The other is when we have an application on the edge which gives advice as to the vehicles, acts basically like a kind of virtual policeman. The enablers which we are using are the MEC and also the V2X broker to exchange information between the different domains. We have one of our vehicles is connected to the TNO network. The other vehicle is connected to the KPN network. The scenario is like this. In the Dutch trial site, we have only a very limited space to perform the maneuver. There we have two vehicles who are driving towards each other, and we would collide unless one of them would deviate from the track. So we have two OBUs which are installed in different SA networks. In the Netherlands, one of the vehicles, the one which makes a deviation, is an automated vehicle. The other is connected vehicle. And in Spain, Portugal, we participated to the overtaking user story, which CTAC has also implemented. There we bring our two OBUs and place them in the CTAC vehicles. In addition, we use an OBU from CTAC, which transmits CAM messages in order to perform this maneuver in an NSA cross-border environment. The architecture in the Netherlands is we have two vehicles, one connected to the TNO network, the other to the KPN network, which exchange data with an MQTT broker in that network. And we also have the MCS app, the maneuver coordination app, which is installed in a virtual machine from Siemens in the TNO SA network. This shows the vehicles. We have the automated vehicle which we're using is an upgraded Volkswagen Touareg, and we have also used the connected vehicles is a TNO vehicle. In addition, we also use the rental vehicles for establishing scenario. Rental vehicles were also used in Spain, Portugal for testing the maneuver coordination. Okay, so we have set of onboard units which consist of a laptop, the modem. In the Netherlands we use the Netgear Nighthawk 5G modem, and then a GPS antenna. So this is fixedly integrated in our automated vehicle and can be placed in the connected vehicles which were used. We have used this approach both in the Netherlands as well as in the Spain-Portugal corridor. And the location is a parking place located in the area which Gert has just shown in between the TNO base station and the KBN base station on the west. Now Julie will start the video.
Yes, I will do so. 1 second.
When you are approaching, try to hit these cars. I'm not scary. Maybe the other driver is much more scary about this. I'm ready.
Hier achter me zie je hoe twee auto's elkaar naderen. en daarbij in een bijna botsingssituatie terechtkomen. Dus de ene auto die helemaal geautomatiseerd rijdt, moet uitwijken voor een andere auto. Nou, dat testen we hier vandaag.
Je kunt vergelijken met de luchtvaart, waar 2 vliegtuigen naar elkaar toe vliegen. Op een gegeven moment moet een beslissing genomen worden wie gaat waar naartoe uitwijken. We proberen dit in een veilige omgeving, dus zonder ander verkeer. En dat geeft ons volledige vrijheid om allerlei scenario's uit te proberen.
That went excellent.
We testen hier vandaag 2 scenario's. Eén scenario is waarbij de ene auto met de andere auto communiceert. En het andere scenario is via ons mobiele opstelpunt. Dus de auto praat via ons mobiele opstelpunt met een Edge-applicatie op een locatie hier 14 kilometer verderop. En die Edge-applicatie die stuurt als een dirigent de auto's uit elkaar. Dus die voorkomt op die manier de botsing.
Wij meten hier hoe het 5G-netwerk gebruikt wordt, de latentie, hoeveel informatie er doorgestuurd wordt, hoe kleiner de latency, hoe betrouwbaarder de informatie is die de voertuigen krijgen, hoe meer kans op succes er is om de botsing te vermijden.
Nou, de kracht van het ecosysteem dat we hier hebben is dat we samen met TNO en VTT experimenteren met deze use case. En hier bepalen we eigenlijk met elkaar de toekomstige standaarden voor het mobiele netwerk om eigenlijk use cases zoals deze mogelijk te maken in de toekomst.
Thank you, Julie. Okay, so here you see some of the results which we have obtained during the evaluation results in September. On the left, you see the latency between the 2 vehicle OBUs at application level, which is when both vehicles are connected to the same network, about 30-40 milliseconds in September. But when the second vehicle is connected to the TNO network, then the latency is occasionally very large. It's more than 100 milliseconds. In good occasions, we have about 50 milliseconds. Then these tests were done in September. Then we did the same tests again, or similar tests again in April. At that moment, we did not have access to the Vaarle parking lot, so we could not do the automated driving tests, and we did the tests on the 8270, driving between from the KPN network, KPN base station towards the TNO base station. And you see that at this moment we have much better results. For the KPN to the TN, when we have both units connected to the KPN network, we have about 20 to 30 milliseconds, and for the TNO network, when one is connected to the TNO network, this is slightly longer. So there have basically no major changes been made to these networks in between. So the improvement in the KPN network is slightly, so we can due to some improvements in the network or in the improvements from the in the modem, but the main difference in the TNO network is mainly due to foliage. So the location which we have, there are some trees and other bushes in between. The TNO antenna is located rather low compared to the KPN base station. So this effect is, at least for the location where we use the test, is very large. Then in Spain, Portugal, we did use a similar software in NSA. The scenario there was overtaking scenario, and we drove from between Spain and Portugal on the new bridge in the corridor. So this shows again the scenario. We have we placed our OBUs in 2 vehicles, and then communicate. There was also the CAM, another OBU in the vehicle, which makes the faster vehicle in fast lane, which makes the first overtake. And so we got this information, and based on this, using the same MCM messages, this vehicle decides when to overtake. We also had the MCS application installed in the Spanish MEC. And this shows here the results. We had issues with the modem. The modems which we have used and also tested in both in Finland and in the Netherlands did not work well in the Spanish-Portuguese corridor. So we had to find an emergency solution, which was the Xiaomi Mi 11 phone, which we installed in the vehicle. And so when we went in March, when we did the tests, the seamless handover did not yet work, but when we compared the results when the vehicle is connected to the Spanish network, compared to the situation where it is connected to the Portuguese network, we notice that we have about end-to-end latencies of about 50 milliseconds in the Spanish network, which is the home network for our SIM cards, and in the Portuguese network where we do roaming, we have only a slightly higher latency. Okay. This slide concludes my presentation, so I would give the word now to Peter Paul, and I will be happy to answer your questions at the end of this webinar.
Thank you, Johan. Peter Paul.
Yes, hello. Are you seeing the main screen or are you seeing the...
We see the other screen with the comments. Now better, yes.
Perfect.
You can see the full screen.
Yes. Thank you. I will explain more about the extended sensor use case as explained earlier by Geert and by Sven. First, I will go into a bit of detail about extended sensors, what and why we do that use case. Then the role of connectivity for extended sensors will be explained. And then specifically for 5G MOBIX, what points will we address in 5G MOBIX. Then the setup of the extended sensor use case will be shown, and we will show a movie about the setup being operational. And then I will go into some results we obtained, both for slicing as roaming, as I will explain a bit further in the presentation, and I will draw some conclusions. Okay, first about extended sensors. Why? The level of automation in vehicles is increasing. We've seen all the movies about the Tesla, Uber, Waymo driving completely autonomous. This is not exactly what we're addressing here. I mean, we already have the automation at the moment on the road on certain applications. Take the ADAS functionality, the ACC, the adaptive cruise control, the collision avoidance, brakes. That kind of automation is already in place. However, this does not always work flawlessly. The vehicles, they rely on their own sensors, the built-in sensors like camera, radar, LiDAR, but they have limitations. They can be obstructed, as you can see in the picture on the bottom right. They can make mistakes, for instance, because the object is a bit unclear, like the traffic sign with the maximum speed in the middle. They can be hampered by weather or darkness, like the picture in the bottom left, or they can even be broken. Also, the vehicles do not always know the current traffic rules. There's static traffic rules they will know, but the map data is mostly static. So dynamic maximum speeds, as in the bottom right, they will also have to be incorporated, and also even lane level accurate. You can see here on the screen, there's a difference in maximum speed on the right 2 lanes and on the left lane. And vehicles do not always exactly know in what lane they're driving, or they detect the wrong maximum speed and will obey that one. And also lane markings, as you see in the bottom middle, they change, and they should also be able to handle that. So This leads to unpredictable behavior of CCAM vehicles compared to regular vehicles, and that leads, of course, to unsafe situations and traffic inefficiency. And they break vehicles due to unclear traffic marking or at least wrong interpreted data. They don't anticipate for emerging vehicles. They break for roadworks warnings because they don't understand the markings, and also they may even get into accidents, or not really desired. That combines with the fact that the vehicle manufacturers, they have acknowledged that their approach of autonomous vehicles, only depending on their own sensors, that they have limitations. So the limitations, as explained before, they recognize that. They also recognize that the GPS is good, but not always usable for exact positioning. It's also a matter of cost, of course. Very high-end models, they can have all the sensors included, and they can detect very well everything around them. But lower-end models, how do they need it? And do they all need all sensors? Can it not be shared? Is there not a more economical, feasible solution? And last but not least, the upcoming possibilities of connectivity and data sharing, they have been recognized. So that leads to the connectivity part, obviously. Everything can be connected to everything. So if this is the starting point, the vehicle detecting pedestrians, bicycles, other vehicles in the vicinity, this is like the current horizon of the vehicle. That can be extended quite a bit with information from the infrastructure direct, from data clouds, from service providers, from traffic management, also from other vehicles. So their extended horizon can be much larger than what the vehicle can see itself. Also, it will help to validate their own sensors. The vehicle on the bottom left, that was already detected by the vehicle in the bottom, but now it gets additional information from the vehicle also showing its existence, and based on that information, the own sensors can be validated. And of course, all that sensor information that can be shared, like car sensor. So all the detection, all the vehicles and other road users, they can be shared and used by all. So now the role of the extended user sensors use case in 5K MOBIX. And so we have seen the potential of connectivity, and among which 5K, that's great. But what exact functionality is now required? What can be provided by 5G? What is still missing? So if we look at the requirements of a use case, of course, there should be sufficient bandwidth and maximum latency. But it should also be working in an operational setting, and not just two vehicles in a completely empty network, but also with other traffic and other road users and normal users in the same network. It still should be using properly. And it should also be working in a multi-operator environment. And of course, and that's the main theme of 5K MOBIX, it should also be working cross-border, going from one country to the other. So that means we need guarantees for the connectivity, and not just the maximum, the minimum bandwidth and maximum latency, but always that performance. And it should be working cross-border, roaming, switching from one operator to the other. So on these two aspects, we have focused on in the Helmond test site for the extended user sense use case. So the guarantees of connectivity and service continuity, and also the roaming aspects. Now for that, we use the test site as already shown by Geert earlier. The network where both the TNO 5G standalone network and the KPN standalone network is available, and with two artificial borders going from one country to the other. And using that setup, we have tested, and you can see on the right, 10 different kind of setups going from the current state with LTE going to 5G NSA, and then adding a 5G SA core from TNO. Then we added edges, and then we added slicing functionality. Then we have the TNO and the KPN network connected to each other, and that has been made bold because we will show a movie afterwards showing the test setup for that specific implementation. And then we go into the roaming scenarios. We have executed the basic roaming, we have optimized roaming, and we were in the middle of the release and redirect steps, which we have identified also in a paper with different steps towards seamless roaming. And as last, we have also tested successfully slice roaming, so going from one network to the other, maintaining the same slice, which is of course important if you want to use the benefits of the slicing. Okay, so let's first go to this movie. So it's a setup with TNO, KPN, and also Siemens. And the goal of this extensive sensor use case is to extend the horizon of the connected vehicle, that's the TNO vehicle. And we did that by a lane merging use case, where we want to merge between a passing, not equipped vehicle and a vehicle fully equipped with sensors and connectivity coming from behind. And that's the Siemens vehicle. So you see here in the screen the three vehicles. TNO vehicles now in front, we have the passing vehicle in the middle, and we have the Siemens vehicle. Here you can see the 5G equipment next to the road with the 5G antennas. And here you see the use case route going from the TNO network, the TNO country, to the KPN country. So to support the use case, we have these two networks from KPN and TNO connected, and that's using the edges, and the edges, they were installed in the Siemens environment as well. So here you see all the information from the Siemens vehicle, CAM messages, and also CPM messages. The CPM messages, they include the detection of the passing non-equipped vehicle, and that's being sent to TNO. But that, of course, is not a realistic setting. That's an empty network. We want to have a real network, so there's a lot of data added to the network as well. And you can see that here. That's mimicking a completely loaded network, and then still it should be working. Otherwise, the service is not reliable. Well, in a normal situation, you would see the effect that you saw here, that the COM and CPM, they are hampered by the data. If you introduce slicing, very simplified, then you can give priority to the CPM and the COM messages, and they are still being exchanged, and the data, the other data, has a different slice and is used differently. Okay, so here we're driving on the road. Here we have the three vehicles going on the route. You see the TNO vehicle, the view from the TNO vehicle on the top. You can see the TNO vehicle in the middle one with a view from the passing car. And you see the view from the Siemens vehicle on the bottom. And it's already passed, but you saw a merging advice. So there is, based on the COM and CPM messages being sent to the TNO vehicle, it knew it could merge, but now it should not, because there is this passing vehicle. And you see on the top, you see also this vehicle now passing. So that's correct. So it's good that it's good information. It's correct. Now the vehicle is going a bit more in the front, and now you see, okay, now it's empty again. So there is a space between the passing vehicle and the Siemens vehicle. So now the TNO vehicle could merge to the other lane. So this illustrates how the exchange of the information between the vehicles extends the horizon or the world map of the TNO vehicle. And that worked properly. Okay, so we did that for all the different setups that you saw before. So the 10 different setups, we have executed the same setup and with the same vehicles driving. Here on the left, you see some results. There are much more results, and there will be in the different deliverables of 5G MOBIX. But here you see some results. On the left, you see the ideal situation. You see the 5G NSA and two 5G setups, and you see the latency, which could be the maximum latency which can be achieved without any other traffic. So you see it around 20-25 milliseconds. That works fine. For the NSA, you see that the delay is higher and also not the same, not constant. If you look at the right side, there we added the slicing, and we also added the lot of other traffic. You can see we compared it then to the results of the empty network. So that's the red spike, somewhere around 50 milliseconds. And you see the blue one, that is the implementation with the slicing, where the V2X traffic is in a different slice than the other traffic. And you see that the performance is almost the same. The traffic is really distinguished from each other. The green line, however, that is if you put it in the same slice both traffic, and then you see perfectly that the V2X traffic will be influenced by the other traffic. So here in one slide you see the possible added value of the slicing if it's implemented correctly, that you can separate one type of traffic from other traffic. So if you look at the use case, and it's maybe a bit complicated slide, so I will not completely explain it, but if you look just at the middle line, at the 0, you can see a yellow line, and you can see that constantly advices are being given to the TNO vehicle. A small circle that means, okay, do not merge, and a larger box that means, okay, you can merge now. But the important fact about, important message about the slide is that there's a constant service being run, and that's because the data is constantly being sent to TNO. It's a reliable service. If you compare that to the other situation where there's no slicing implemented, or at least there was one slice and all traffic is in that slice, if you look at the same middle line, you see that it is really different than from the previous slice. And there's sometimes an advice, but sometimes there's no advice whatsoever. So it becomes clear that the service is not reliable, not usable like that. If you do not receive an advice half of the time, you will not be able to depend on such a service. So this is the test that we did for the service reliability. I would say the continuity, that it works as expected. Some other results, what we obtained is for the roaming. Some first results to share. As said, the other important part is if you go from one country to the other country, it's important that the service will continue to work. And at the moment, as we know it, also with 4G, that there is an interruption to go from country A to B. So first we had to implement for 5G as also a roaming setup from going from TNO country to KPN country. If you do that just plain with no optimization whatsoever, you can see that there's an interruption time of a bit more than 1 minute. So that's just like the black circles. Then we've implemented a couple of improvement steps, semi-optimized and optimized roaming. And you can see that the interruption time drops already significantly towards like 10 seconds. Now 5 seconds maybe even. So in that order. That's still not enough for a service to be running, but it's heading in the right direction. In the paper that we've written, that there is more steps towards the seamless roaming described, the release and redirect, and that should mean in the end that the results that we attain here will even be lower. Now you will release the connection and you will directly guide the vehicle to the next network. Now it will have to search again for the next network between the whole band. So there are different possibilities to even improve it further. That will not be part of the 5G MOBIX project anymore, but we hope to continue that in the next project. So to summarize the results, the 5G SA that really reduced latency in general to 5G NSA. The routing also reduces, so that's the first plots that you saw. But the slicing functionality, that will be essential to harvest this potential. If you have a low latency but not reliable, then it still will not work. So the combination of that is essential. Well, we have tested all kind of different setups to show that it works, and it also is possible to hand over from one network to the other, maintaining the same slice or slice quality of service. Also, we have executed the first steps of slice roaming and the first improvements to lower this roaming interruption time to acceptable levels. But depending on the use case, of course, it should even be lower than we have realized now. So we have described at least the next steps which will be necessary. The point is that this functionality is not yet available, not in commercial equipment, but also in experimental settings that will have to be additionally implemented after development. So that was my presentation on the extended sensors. So I would like to give the floor to Josten Oude for the third use case, the remote driving.
Thank you, Peter Paul.
Thanks, Peter Paul. Can I take over screen? Yes, thank you. Okay. Hope you can see my slide.
Yes, yes, we can.
Okay. Thank you for confirming, Savi. Okay, thank you, Peter Paul. Yeah, so again, my name is Jules de Noude. I am from Eindhoven University of Technology, and I represent here the work that we've done together with the rest of the partners in the remote driving use case in the Netherlands. So to summarize, we have our use case partners. So in this case, we have RoboAuto, who is actually providing the remote driving technology, mainly the software for that. We have Siemens, who provided a vehicle in this use case, but also provided the virtual vehicle setup, which is based on their tool sets pre-scan. We as TUI were also together with one of our spin-offs, AI Emotion. We set up and provided one of the remote driving vehicles and a remote station. And we have been working on a separate standalone network which focused on localization using millimeter wave. KPN was involved in this particular use case based on their SA network that has already been presented by Geert, but also by Peter Paul and Johan in their presentations. And TNO was involved regarding part of the slicing, which we also apply to this particular use case. So I will go first into some of the key features of remote driving. I will not go into the full details of the business case for what the remote driving is. I will focus mainly on what the technological implementations that we did, and also the trial executed, and I will provide some results for each of the trials that we did. So if you look at remote driving, then you basically are trying to mimic this part where a normal driver is taking over the steering wheel and the throttle of a normal vehicle, and that has a certain delay already. Yeah, so there's a delay in how a human reacts to what he sees. There's a delay in how quickly he can actually respond. So I'm giving here an kind of an input of what we are comparing then remote driving to. So if you then look at what remote driving is, you already have some inherent delays, which causes basically how quickly a vehicle can come to standstill, for example, or how quickly a vehicle, for example, can take a certain maneuver. So now with remote driving, we're actually deliberately adding some delay to that. There's basically, you add a camera to a system, you add compute power to the system that needs to actually encode and decode the video stream, for example. But we're also adding a communication delay by adding, for example, a 5G network or 4G network or whatever you like. So if you look at 5G MOBIX particularly, of course, and remote driving in this sense of 5G, we're focusing on these two parts where we are trying to minimize this delay as much as possible. So why is this important? Well, especially in remote driving, of course, you can imagine that you are trying to stream video from a vehicle towards a remote driving station. But at the same time, you're also sending driving command data back to the vehicle in order to take control of the vehicle. So this is a total entire closed loop that needs to be as short as possible to make sure that at least the control over the vehicle is as natural as possible. Well, there's multiple ways to do it. I will go into that a little bit in the rest of the presentation, but one of them is at least also adding slicing, which is one of the things that I'll discuss. In our setup, we had basically 2 remote stations, two vehicles, so we could also do some testing between different switching between one remote station to one vehicle, another remote station to the second vehicle. But we also had a gateway which could actually control this. So this was basically pre-built. We did not focus on actually optimizing that part, because in the end, it's making sure that you have that peer-to-peer connection, and then when that connection is there, you have to make sure that it's still stable. So if you look at what we've done, and I'm focusing here mainly on the trials and on the test that we executed to figure out, okay, what is actually required on one side for remote driving, and on the other side, what does it mean for the network, is that we focused on a few application level KPIs, which is on one part as checking what is actually compared to manual driving, what is the impact of having this screen resolution and video quality, and also what does that then mean for decoding and encoding of the video signal, and therefore also what kind of impact has that for your network. We also heavily focused on trying to research and find a methodology of seeing what the impact of a communication delay might be on actually the position of the vehicle, because in the end, the only thing that you're trying to do in remote driving is position that vehicle safely, and you want to know that, of course, within a certain boundary error. That relates also then to, okay, but what does that mean for your network? What kind of impacts does that have for your network? So we try to focus on seeing whether or not we can improve that latency part by introducing slicing, like Peter Paul just introduced already. And fourthly, we also focused on using actually our millimeter wave network to also focus on, can we then go one step further and see if we then also use such an existing network and see if we can use that actually for positioning. Like Peter Paul in his previous presentation already said, OEMs have, of course, access to GPS, but in certain situations, GPS is not always as accurate or always as good as it aims to be, especially in an urban environment, or, for example, in a cross-border setting where you might not have the best coverage. Can you then cover this, for example, with a 5G network? So let me first introduce the first two application level KPIs, and then afterwards I will go into those network KPIs. And what we've done is basically we try to focus on both doing some virtual testing, so in simulation, as well as real live testing. So first of all, we focused on making a comparison, also better understanding of what is important for remote driving, and actually making sure that the position accuracy of such a vehicle can be met by comparing our setup, our current setup, also as a kind of a benchmark with what normal manual driving is. So you see here in this graph, basically in the solid nights are all the tests that we've done with different kinds of drivers, but also trying to figure out, can that person detect a certain obstacle that he needs to deviate from in time. And typically what you see already from this graph is that this is very much on implementation level. Yeah, so I have to give a little bit of a disclaimer here. This is very much based on, of course, our setup that we used, but it gives a little bit of an idea about what you need to consider more than only the network delay. What you see here already very quickly is that if you compare just a manual driven car with a remote driven car, we already have very quickly the fact that a person using a remote driving station has far more difficulties actually in detecting a certain obstacle in time. So obviously this has safety implications, because if a normal driver can detect a cone in this case already 200 meters from now, but the remote driver cannot do that, but only can detect that cone after 100 meters, then you have to take that into account, of course. What you also see is that while we did some testing here with actually reducing the resolution of the remote driving application, in order to see what kind of impact has that then on your bandwidth in general, of course, but also what kind of impact has that also on the performance, on the driving performance. And you already see that when you halve the resolution, then an additional 11 meters is lost already in this case. So this gives an indication of why it is important to have a good high resolution image to a remote station, and also what that means for the network basically. So basically you want to stream ideally high resolution images, but also good position camera positions to that remote station. So second one we did in testing was, okay, we know this a little bit. Let's focus then on actually introducing artifacts into the network itself. So let's see if we can induce artificial delays basically into the remote station application itself, and see what kind of if you induce such delays, communication delays into the network, what kind of effect that has on the remote driving experience, but also therefore on the safety and the position of the vehicle again. We first did this in a virtual setup, so and afterwards we tested that actually in real life. So what you see here is two videos. On the left side you see a network that is no disturbance at all, and then on the right side you see a network inducing where we have a 20 millisecond delay. And you already see very quickly what that has for impact on packet drops and etc. And also again then what that can give as an example for the stopping distance. So in this case we focused on two different kind of tests. We did the straight line braking test, so see how far actually you stop the vehicle, and the second one is a similar one. On the left one, no disturbance at all. On the right side we have some disturbance, doing a slalom test. And why is this slalom test interesting? Well, in a sense, basically, you're talking about a sine wave, yeah, slalom. And typically, if you have any control background like myself, then you know that when you introduce some delay into a system, into a feedback system, then there will be a phase shift. So basically, your entire sine will actually start shifting in time. You can see already that the right-hand driver already has quite some difficulties getting this vehicle in line as he expected to. So this is already some things that we done already more than a year ago. We also ported this into real life. So that is a video what I'd like to show. This is on the same test site as Johan showed his cooperative collision avoidance setting. So we basically took this test site where also the cooperative collision avoidance part was tested. And we did multiple tests here with the KPN network, on the KPN standalone network, in different times of year, and also multiple times to also see what kind of improvements were there on the network side, etc. Focusing here, indeed, what you see here is the two vehicles. So this is our TOE and AI emotion vehicle, with Geert actually in the back showcasing what kind of equipment we have in the back. Using a WNC 5G modem in this case for the communication. And this one is showcasing the Siemens vehicle with the DirectPX2, where we had our remote driving software running on. So all these tests were executed with safety drivers. This is Victor Ho, who's actually stepping into the Siemens vehicle. I see he's also in the webinar today. Hi, Victor. So we try to really reproduce this kind of testing and try to figure out, okay, what kind of influence does the network have on this kind of application. And again, we deliberately chose these two tests because this can say something about the impact of a communication delay on such an application, and also therefore on the accuracy of the vehicle position. So what you see here is that Siemens vehicle does here some stopping distance tests. And we did this at different speeds. It's 10, 20, 30, and 40 kilometers an hour. So from afar, it looks like very slow. I can tell you when you do this as a remote driver, it's far more difficult to understand what the impact is of what the vehicle does. So a little bit later on in the video, you will see me indeed doing this kind of testing. So we've done quite some tests on this. This kind of data will be also made available later in the project. So for further verification, but also for further research, of course, outside of the consortium, to give a little bit of an understanding. So to give you a little bit of an idea, what we've done in order to evaluate this is we looked at then the position of the vehicle with respect to those cones. Like I said, especially I'm focusing here on the slalom only because that tells the story best. If you expect a delay here, then you also expect that your maneuvering of the vehicle will be delayed in time and therefore also in position. So if you then compare indeed manual driving with, we did testing on 4G, but as well also on 5G, you basically always see indeed that there is a delay. So here I am talking about a delay in position. So typically we see here that the vehicle is at the first cone already 1 meter later turning into the corner than you would expect with a manual driven car. And the faster you go, of course, the more difficult it will become because the sign sweep will become unstable, and therefore it will become much more difficult to also get those cones. However, what we noticed is that, so yes, we can say basically that there is an influence of some delay somewhere, but however, we could not really find a clear, distinctive difference between our 4G implementation and our 5G implementation. So that we also focused on checking then, okay, what is then the latencies that we see actually on the network. So we did go down from 4G implementation to 5G implementation from 25 milliseconds roughly to 15 or 10 or 15 milliseconds. Also on the control uplink and the control downlink, which is basically the commands that you send from the steering, from the remote station steering and throttle to the car, those were also improved. But since these are so small of a part of the entire pipeline, in this, at least in this particular implementation, it was very difficult for us also to say that really had a significant influence. What we did see, however, is similar to what you saw in the virtual test setup settings, is that when there is packet drops, for example, we did indeed experience issues with the radio signal being blocked by, for example, those leaves and trees. Then, of course, you will also see that directly into your end results of the data. All the results of this part of the presentation, by the way, is published in a journal that is already public since January. So the link is also in this presentation. So then if you know this kind of things, then it's interesting to see, okay, what can we still improve on the network side? Regardless of whether or not we can say something conclusive about it, we know that we can at least focus also on really improving the network, because it will be that the network will be polluted by other traffic. And as Peter Paul already introduced a little bit, is slicing is one of these solutions here. So we also focused, the colleagues of TNO at least focused on doing some testing with the remote driving setup, where they focused on looking at the throughput of the system. So in this case, it's a fairly simple test. You have one vehicle which is connected to Geno B and the core, and you see what is the maximum bandwidth that it can achieve. But then if you introduce another polluted system, so basically another UE that is actually broadcasting data with also 20 Mbits, then you suddenly see that you will get a performance drop of this blue line, which was first at 15, is now dropping back to 11. But then if you add some priority slicing into the system, you can basically solve that issue fairly simple. At least that's what I understand. So basically, Paul can explain this better than I can. Into the system where your original video stream signal can go back to its original throughput. Finally, from TOE's side, we also have been focusing in the past years on actually focusing more on improving positioning using beam angling. So what we have been focusing here is actually that when you assume that you don't have any GPS coverage, can you still get accurate positioning information from the vehicle? So in my last slide, I've combined actually the summary of what we've done so far. We've done some testing on the TOE campus. You see here on the right side, basically a setup that showcases a base station, an end user, in this case, the vehicle, and then on the right side where that was, showcasing what kind of information from the radio signal we get. So you have basically your line of sight signals, your non-line of sight signals, and that kind of information tells something about how well we can cover it. What we've done in simulation is see how far and how accurate we can position that end user then using both of these signals, so the line of sight signal and the non-line of sight signal. And in our simulation so far, and we want to actually improve that later on by implementing the radio measurement data that we've collected recently. But so far we can estimate to having up to a 30 centimeter accurate error, at least position error, on a distance between the base station and the vehicle. So that's basically summarizing the work that we've done in remote driving. I would like to give the floor back to Sven Jansen.
Thank you, Jos. Sven, the floor is again yours.
Yes, okay, thank you. Maybe I should put on my camera so people can see me. Let me go to the slides. There are quite a lot of slides today, as you can see. Summary. Okay. Yeah, so the summary is quite short, but so it's quite high level. So if you have any detailed questions, once again, feel free to put them, to register them. So when we look at the use case of the trial site, we've been addressing roaming, interruption, service continuity, and position accuracy. So that's really some main functionalities. This functionality has successfully been implemented for the different automated driving applications. We also have seen results for many variants of the networking setup. On the one hand, it's sometimes difficult to compare directly the results from different sessions, but we can really see what kind of improvements have been made during the evolution. And actually, we did about 10 different network configurations in the Netherlands, so we can see what the different technologies bring. Then the third bullet is quite important, since and the main focus of 5G MOBIX is to look at cross-border issues. For that, we have been linking to the Spanish-Portuguese trial site, and we have successfully transferred technology there. We have actually two different types of networks. So in the Netherlands, we use standalone networks, and in Spain, Portugal, it concerns non-standalone networks, as also presented by Johan. Yeah, and then slicing is a big topic for 5G. So we have assessed the benefits of using this technology for high payloads, looking what does it mean in terms of the networking performance, and what is the implication for automated driving applications. So that is in summary what we have done, and yeah, I'm looking forward to any questions that there are to answer by the panelists.
Thank you, Sven. Well, thank you all for your input and your presentations. Indeed, we're now opening the floor for a discussion, and we're ready to receive your questions. So please feel free to type your questions to the question box. You can also indicate the speaker you're directing the question to, and we will collect them and address them as we go now. But as we allow some time for you to formulate and share your questions, perhaps I could ask a question. I have a question for Geert. How we already have phones available with 5G. That's something that I know. How does the 5G MOBIX setup compare to the 5G networks that are being deployed?
Yeah. So currently, what we have in Europe mostly is we're using 5G new radio. So the radio that we're using is based on 5G, and the core systems are still using 4G networks. So it's an additional to the current networks. Within the 5G MOBIX projects, we are testing it, at least in the Netherlands, testing with also 5G core systems. So both radio and core systems are 5G. This way you can also use all the newest features that are available on 5G, like for instance slicing, which is only available using a 5G core. So I think that is one of the main differences between regular or current networks. And I think we see that new networks will become all based on 5G core, will become available in the coming years. So that is still some time before it really becomes mainstream in Europe. Yeah.
Thank you, Geert. Very insightful. And perhaps a question for Peter Paul. Many network variants have been tested. Which change do you think made the biggest improvement, or what do you think should be done first, or should have been tried first?
It's quite a broad question. I mean, indeed, a lot of setups. I mean, if you just look in terms of latency, you can see from, well, you could have seen from the plots, but they were there pretty shortly, I have to admit, that already quite some improvement can be made going from the 4G to 5G networks. But the implementation of the slicing, that really showed that you can get that benefits all the time. So I would say that if you would like to have low latency use cases in the mobility world, that kind of functionality is essential to get the real benefits from 5G. The other answer for the roaming kind of aspects, if you can see, we now kind of pre-programmed the SIM cards mainly, and to lower the interruption time, really quick gains can be achieved if you guide the users directly to the next network. You explain what is the next network, in what frequency band you can find this network, instead of that a mobile device or a vehicle has to search itself all the time, completely scanning all the bands and then make a decision of where to ask permission to roam to. So a lot of can be gained by already explaining the user where to go to next.
Thank you, Peter Paul. Now, Jos, how demanding do you think is remote driving given the networking capacity? What do you think is most critical, the low latency or perhaps the data limit?
Well, at least in our research that we've seen is that so in our use case, yeah, we had of course a preset implementation. So we focused on basically seeing what kind of impact that has on the from the network side on the application. But if you look at where the most where you can actually achieve the most is actually trying to reduce the decoding and encoding part. So basically, if we can stream with as much as possible the highest bandwidth data basically over the network, that would hopefully improve a lot of the on the application level side the delay. Yeah, I think in that sense. Does that answer your question a little bit, Sabi?
I guess so. Thank you. And perhaps one last question for you, Johan. For MCM, there is a coordination of the vehicles. Who should be coordinating on the vehicle or, for example, at the network edge?
Yeah, we tested two different approaches. One is that the vehicles communicate directly with each other without any application on the net. The alternative is that you would have a kind of virtual orchestrator, policeman who directs all the traffic. So in case you would have a lot of traffic, the second approach may be beneficial, but requires that the road operator or another partner would have the application on the edge. In case there is not such an application, then it would be the responsibility of the vehicles to find a solution between themselves.
All right, thank you so much, Johan. I believe we have come to the end of our planned agenda for today, 5 minutes earlier. I don't see any questions coming in. Oh, perhaps this is one. What are or were the biggest challenges realizing the 5G SA setup? Is that something for Sven?
Maybe that's something for Geert, I think. That's the MNO in there.
Yeah, so I think one of the major challenges, especially in the beginning, was the technology. When we started, was quite new, and we are sort of depending on the vendors for providing the new technology. And still, we see not everything is available yet. So when looking at SA cores, we're using them now, and we are using mostly some versions that are still quite new also from the vendors. So sometimes more trial-like versions. Still, for instance, roaming is currently not yet standard available from the vendor side. Also, the device side, if you buy a regular phone in the shop, it will probably do not SA. So you need to really configure it for SA or hope to find a phone that is configured by default from the factory. So I think the availability of new technology is I think the most challenging part. And we would like first also to test the real handover part using SA set up in our network. But yeah, this is not yet available from the core perspective. So TNO have developed our own core, added interfaces to it to be able to test such a thing. So I think that is probably the most challenging.
Yeah. Maybe to add to it, there's indeed, I think, quite a discrepancy between what is being suggested, especially in the beginning of the project, in terms of what 5G as a functionality is already available and what was actually available. So also not just in the core network, as Geert explained, but also for the UE side, so for the equipment in the vehicles, it was quite difficult to obtain elements, obtains onboard units to be able to test with, and especially onboard units in which you can have all kind of logging and debugging functionality. So that was, I think, indeed the biggest challenge, realizing all the setups.
All right, thank you, Geert and Peter Paul. Do you expect that it will become available everywhere in the future, the 5G SA functionality?
Sure, it will. Everything, but with due time, it will become available. But it takes time. So you see that in different, for instance, GSMA is finalizing, I think, also the roaming part between operators on SA. Then the MNOs have to start implementing it. I think most MNOs probably have started it. But before it will become available, it always takes some time, and you have to. I think most phones still work on 4G. So before we really get a large base on the SA part, we probably are some years ahead, maybe 3 years so before it becomes mainstream available.
Good to hear. All right, I think we got to everyone and the questions, and thank you so much for your input and answers. We're closing just in time, very efficient, very effective, very Dutch as well. Thank you very much for your participation, and to the audience, and thank you to all the speakers for your interesting remarks and questions and being part of this event. Is there anything else you would like to share before signing off? I'll take this as a no. And yeah, before we sign off, I would also like to remind you that there is an upcoming webinar coming next week that is focusing on the South Korean trial site. And as I previously mentioned, there were 3 previous webinars also that took place the previous days. So you can find all of them and the one and the webinar recording of today on the 5G MOBIX website on the link that you can see on the screen. And yes, I would like to thank the speakers again, and hope to see you next week, and wishing you all a great rest of your day. Thank you.
Okay, thank you.
Thank you.
Thanks for hosting.